Hi class, it's your teacher Miss Green once again. I'm going to walk you through a slightly more difficult balancing equation problem. When you first see this, you're probably saying, what in the heck is this? How do I even start to approach this? Okay, which is completely fair. So I'm going to walk you through how Miss Green would approach this. First things first, when I see this guy here, okay, the CH3OH, this is what is called a structural, formula. So it's indicating that this OH, okay, is on the end of this hydrocarbon to show that it's an alcohol, okay? And so we can rearrange this so all the hydrogens are together. That's probably what I would do. So it's a little bit easier to see how we're balancing these out, okay? So I'll rewrite this as CH4O, okay? So these two things are exactly the same. This is just kind of giving an idea of how this molecule arranges itself in 3D space, indicating that this OH is right on the end, but for our purposes, since we're trying to balance this equation, we can go ahead and rewrite it as this. Okay, so just like we've done in the previous examples, first thing you probably want to do is make a T-chart so we can go ahead and start our bookkeeping process. And so we're just going to go from our reactants to products and count up how many of each type of atom we got. Okay, so on our left side we have aluminum, okay, and we got one of those guys. We have chlorine, and we got 3 of them. And then we have our carbon, which we have one of those. We have our hydrogen, in which we have 4 of those. And then we have our oxygen, in which we have just one of them. Okay, we're going to do the same sort of bookkeeping with our products. So we have aluminum also on this side. Okay, we only have one of them, so that matches. This might be a little bit scary looking, but all this is saying is for every 1 aluminum, because keep in mind, aluminum usually takes on a 3+ charge. So for every 1 aluminum, we have to have 3 of these polyatomic groups, okay? That's what this little 3 on the outside means. So we have to have 3 of these connected to the aluminum to make it feel neutral. Okay, so how we're going to work with this 3 on the outside is we're going to distribute it to the innards to count how many atoms of each then will be there as a result. Okay, so we'll have 3 oxygens. So oxygens, we got 3. We'll have 3 carbons. So already you can see that we're not completely balanced here. And then we have 3 of our H3s, okay? So if you can imagine in space, we have 3 hydrogens for every group. And if we have 3 groups, 3 times 3 makes 9 in total of our hydrogens, okay? Then our hydrochloric acid over here, this hydrogen now will add to our total number of hydrogen, okay? So instead of 9, this side is gonna be 10. And then for our chlorine, we have one of those, okay? So this might seem a little overwhelming and like a lot, but believe you me, you'll be able to do this. I am certain, okay? So the first thing that I probably want to do is find probably the least complicated species out of all this. And for the most part, I think the least complicated is going to be our hydrochloric acid here. This is the HCl. Our H's, as you can see, are very different, and it might be difficult to see how we can manipulate the left side in terms of H's to match the right side. So what I'm going to hone in on in terms of our parts of our hydrochloric acid is going to be the chlorine, okay? So the chlorine is 1 on the right side, but I have 3 chlorines on the left. So I'm gonna go ahead and just for fun, I'm gonna throw a 3 out front of this, and keep in mind that this 3 is not only gonna distribute to the chlorine, but it also needs to distribute to the hydrogen, okay? And so don't let that scare you that this number is big and it's gonna get bigger, okay? Don't worry about it. So 3 times H is 3, and then we already had 3 times 3 H's, which is 9. So what that means, okay, is this is going to change. We have our 3 times 1, which is here, 3 times 1, plus the 9 H's that occurs from this polyatomic group, okay, for a grand total of now 12 hydrogen atoms, okay? Now we can take a look at our chlorine, and that's kind of what we wanted to manipulate to begin with, is we have our 3 times chlorine, okay? So that means times 3, that goes away, and now we have 3 chlorines, okay? So let's do a quick sort of atom check, bookkeeping check, or vibe check. All up to you how you want to describe this. We have 1 of our alumina, we have 3 of our chlorine, we have 1 carbon and 3 carbons, so we know we need to do something with our carbons. We have 4 hydrogens and 12 hydrogens, so we definitely need to change something with that. And then we have our 1 oxygen and 3 oxygen. So you may or may not have noticed, okay, the atoms that still are unbalanced on our left-hand side all of them belong to the same species right here. So we need to find some way to manipulate this specific species, okay, to see if we can get it to line up with the number of carbon, hydrogens, and oxygens on our right-hand product side, okay? So what I'm gonna look at first is probably the number of hydrogens, right? Because that's gonna be the biggest number we gotta match. And so I'm gonna see if I can get that to match up, and hopefully our other 2 atoms will kind of fall into place. So when I see my CH4O, right, I have my 4 hydrogens, and I'm thinking, what is the common multiple between 4 and 12? So 4 times 3, so let's put a 3 right out front here. Okay, so 4 times 3 is 12. Okay, so when I put a 3 out, that's going to change this to times 3, leaving me with 12 hydrogens. But because we have 2 other atoms also within this compound, we need to go ahead and distribute that 3 to those guys as well. So 3 times carbon, okay, just 1 carbon, so 3 times 1 times 3 will get us a total of 3 carbons, okay? 3 times oxygen changes this from 1, we are multiplying by 3, we now have 3 oxygens, okay? So it appears that we might have a working set of coefficients. So just like we did in our last example, if we did not manipulate a species, there is going to be an implied 1, okay, because it's 1 mole of that particular species, okay, 1 mole in front. So if I were to ask you a question of what are the coefficients that will make this balance, you'd say 1, 3, 1, 3. So let's do one last vibe check to make sure that we are matching on both sides. We have 1 aluminum, 1 aluminum. 3 chlorines, 3 chlorines, 3 carbon, 3 carbon, 12 hydrogens, 12 hydrogens, 3 oxygens, and 3 oxygens. So this honker of a problem is a balanced. So hopefully this was helpful for you. I would say try and apply the same type of logic to your stoichiometry homework, and hopefully you'll kind of make this second nature. All right, see y'all next time. Bye.